Well, it's all right.
This meeting is being recorded.
Thank you.
I already censored myself, took out various things that I would have said if we weren't being recorded.
Oh yeah, okay, public. But of course, nowadays you can always edit it out. If you,
You can try. Yes.
Yeah. Right. Welcome to lecture 27 of experimental math taught by Dr. Z at Rutgers University. Today we are pleased and honored to have the guru, Dr. Neil Sloane, who will give a guest lecture. Let me just do in terms as a brief remark. This is experimental mathematics, and there are two major tools in experimental mathematics. One of them is computer algebra system, a Maple Mathematica Sage, and the other, possibly even greater, is the online encyclopedia of integer sequences. Go ahead.
Thank you, Dr. Z. Okay, so I should start by sharing screen, and let's go here and to share. And there is my first slide. Thinking about this talk, I changed the order a little bit, so I'm going to leave it in this mode for the moment. So this is going to be an illustrated guide to the OEIS with many unsolved problems. And I'm going to start off by telling you some of the basic things about the OEIS, about the editing process. And then I'm going to talk about a very famous problem that we made a lot of progress on recently, and that's in the other topics. But then I'm going to come back and talk about the editing process. Maybe I'll do that after submitting and so on. Then I'll come back to gerrymandering and facial recognition, which I think you'll love, and the LES family of sequences, lexicographically earliest sequences with various properties. So the OEIS, the basic things you need to know about the OEIS is, one, this is not social media. This is a scientific database. You don't call yourself Bobby Joe Jones. We want your real name as you would put on your driver's license on your publications. And what we have in this database, we have very accurate information about 350,000 sequences. For each one, you get definition formulas, programs, references, links, and you can look at the sequence as a list, a table, you can play it, you can look at the graph of it, you can play it as music, you can play it on the clarinet, or the piano is the default. It seems to work pretty well. And we get about 30 new entries, 50 updates every day. We get about 1 million hits a day. There are 10,000, we just passed 10,000 citations in the literature of the OEIS. People say it's one of the best math sites on the web, and I agree. And I began it in 1964. We have a lot of not quite enough unpaid volunteer editors who do the editing every day. We get a stream of submissions, and we need more editors. And I'm hoping that eventually some of you may become editors, because it really is interesting. So the database lives at oeis.org. It's owned by the OEIS Foundation. We're a 501c3 charitable foundation in the US. And we don't just do sequences of integers, we do fractions. We separate the fractions into numerators and denominators. So for instance, the Bernoulli numbers give rise to 2 sequences, one for the numerators and one for the denominators. The Bernoulli numbers being fractions, they're not integers. We do decimal expansions, we do triangles, arrays, and so on. And since last year, Russ Cox is now the president, and I am the chairman of the board. And so here's a classical example of a sequence, and I'm going to come back to this a couple of times in the talk. It's one of my favorite sequences. It's the EKG sequence. It's called the EKG because it looks like what you see when they measure your heartbeats. It goes up and down and up and down in a not quite regular way. And the definition is very simple. The first 2 terms are 1 and 2. So here is the beginning of the sequence, 1 and 2. And then the rule is you always pick the smallest number that has a common factor with the previous term. So after 2, we've got to have a number that has a common factor with 2, meaning an even number. And we always pick the smallest number that we haven't used already. So 4 works. And then again, another even is required, so 6, and then 3, and so on. So it goes up and down. And when you click the graph, I'll show you what happens in the next slide. Another thing that you note is the offset. This starts with term A of 1. So it's got offset 1, and that's what this offset means. People find it a bit confusing. The second offset is something you don't need to bother with right now, but it has to do with the lexicographic ordering of all the sequences in the database. And very often, the sequence itself, the data section, will give you about 4 or 5 lines of terms. In the old days, the limitation was 3 punched cards. But now we've gone beyond punch cards, and you can put more terms into the data section.
And in 1964, it was punch cards.
Yes. Yeah, it was. It went from file cards, little 3x5 cards, to punch cards, and then it evolved over the next, 47 years? And now it's a wiki. Oh no, we became a wiki after 47 years, yes. And the other thing you notice, very often, the first link is what we call a B file, which is more terms than you get in the data section. Typically 10,000 terms, sometimes more, sometimes less if we don't know many terms. So the B file is a list, a numbered list of the terms in typically 10,000 terms. And if you click the graph button, you get 2 plots. You always get a pin plot of the first 200 terms that you can see there. This is the EKG sequence. If you click graph, you see 2 graphs, a pin plot of 200 terms, and then a dot plot, a scatter plot of however many terms are in the B file, all the terms we know, whatever that is, in the B file or in the data line if there is no B file. And this one has a very interesting graph. It's got 3 straight lines, pretty straight. They're not really straight, but they're straightish. And one has slope, 1 and 2.5. And we don't actually have a proof that that's the case. This is an unsolved problem. Prove that the sequence lies on these 3 straight lines. Jeff Ligarius, Eric Rains, and I proved that it's bounded by linear bounds, but no one has ever been able to prove that. The fact seems to be that all the primes lie on this line here. Anyway, here's another version of the definition. And that this was sent in by a high school student, invented, you can say, by a high school student in Birmingham, England in 2001, and Jonathan Ayres. Pretty nice sequence. And there's a reference to our 2002 paper 20 years ago. But this is a really good sequence. There was a colloquium talk at Rutgers last week by Heather Macbeth, who was talking about using proof assistance in teaching mathematics. And I would like to propose as a homework project, in quotes, to someone, it would be nice to have a proof that the EKG sequence is a permutation of the numbers 1 up to, a permutation of the natural numbers. This is one of the things we proved in our paper. It's not that hard to do. You can do it in your head. It's a few steps. It's a little bit tricky. There are maybe 6 or 7 or 8 steps you need to prove this. You don't have to do any integration, but you need to follow a logical proof. And this one, we can prove it's a permutation. It's not that difficult. But there are several other LES, lexicographically earliest sequences, where we don't have a proof that they're a permutation of the natural numbers, that every number appears. These sequences all have the property that you can't have repetitions. And the hard part is to prove that every number appears. Prove that, 193 must appear eventually. That's the hard part. And for the EKG sequence, you can do it. It would be nice if someone would write out a proof that this is a permutation using one of these proof assistants. Professor Macbeth talked mostly about a new proof assistant called Lean, and you write out the proof of your theorem in Lean, and then you can be sure that you actually have a proof.
I respectfully disagree that it's a good idea. I'm not a big fan of this form of proof. It's like pig Latin. They take a human-generated proof and then they transcribe it in a painstaking, very tedious way. So it was very good when Gautier did before color. So it was fun the first time. But that doing it for any human-generated proof is just a waste of time, in my humble opinion. Sorry.
Yeah, I agree. No. But the advantage of doing this is that it might help in proving that some of the, and even to check that I have had many proofs in my head of that these other sequences are permutations. But then the next day you think it through and you say, all right, there's a gap there.
Okay, that's a good use. But it's very tedious, so I don't.
It's very tedious. That's why I'm hoping the students will do it. Yes. Yes. All right. What was the other thing I wanted to say about this? I can't remember. All right, I'll move on. So the second part of the talk, I'm going to talk about the editing process, because this is something that actually is really important, as I will explain. So the database, how do you submit something? At the bottom of every page of the OEIS, every web page, there's these few lines, and where I put the pointer there, you click contribute new sequence, and then you get a dialogue, a series of boxes that you fill out, and then you submit it and the editors look at it. So submitting is easy. You have to register first, and you register by clicking on the register button. Another thing here I want to mention is that there's a button here called plot to, and this enables you to plot one sequence against another, or a sequence against a shift of itself. And this is a different way of looking at sequences besides the usual graph function, which actually can be very useful, as you'll see in a minute. And you can see it tells you how many sequences we have and the license, blah, blah, blah. All right. What about the editing? So the great thing about editing, as a mathematician, it's very hard to find new problems to work on, because all the easy problems and most of the hard problems have been solved already. The nice thing about the editing process is that people who are not professional mathematicians usually send in problems that they've been working on. They've worked out the first few terms of a sequence. Usually they have not done much work on it. They don't have formulas necessarily. So this is a great way to find interesting problems to work on. The kind of problem that you just say, all right, I'm not going to do any, this is something I really need to solve. And you don't do anything else for several days. It's dangerous, but it's very interesting. And so the editing process, if you're an editor, or even if you're not an editor, but just somebody who's interested in helping, you go to the webpage, oeis.org/draft, and you see a list of the proposed sequences and comments that are waiting to be approved or disapproved by the editors. And typically there will be about 350 things waiting to be approved. Usually I see 4 pages of stuff. And they're arranged in order by the most recent at the beginning. I did this on April 16th, and you can see they're submitted by various people, and you can see their limits. Here's some one of 15 submissions by Maximilian Hassler. He's an editor-in-chief. He has a limit of 19. That's a good sign. Chai-Hua Wu, another really excellent editor. We've collaborated a lot. And ordinary people who've just registered have a limit of 3. Some people have intermediate limits. So that tells you. And then you can see over here that they've been edited or partially edited by editors or even non-editors. I think anyone can edit. If you're a registered user, you can look at this stack, and I recommend it. That was page 1. After 4 pages, you get down to the bottom of the stack, the things that have been waiting the longest to be approved. And that my job usually is to clean up the bottom of the stack, the dregs of the stack, well, or just things that have been kicking around. The editors have made suggestions. The editors will say, look, that's not clear. What do you really mean? And that usually takes a number of exchanges and takes a while. So you can see down here, they were at the bottom. When was this? The last one there was submitted March 8th, and it was still on March 8th. It looks like it hasn't been touched. So I would have dealt with that. I looked at the bottom of the stack almost every day and clean up some of it. So that's the stack. And then what happens? Well, so here's a lovely example of a sequence. It was submitted by somebody I don't know in February. Roughly speaking, this sequence, we only know 4 terms, 1, 8, 146, 4294. And what the 8 is, it's the number of expressions you can make. It's the second term. It's the number of expressions you can make with 2 letters, combining them in all possible ways, using the operations of addition, subtraction, multiplication, division, and exponentiation, and using parentheses if you want them. And there are 8 ways of combining 2 numbers, 2 variables, 2 operands, A and B. You can have A plus B, you can have A minus B, you can have B minus A, which is different, and so on. There are 8 of them. And if you would like a little job, folks, compute some more terms. We don't have any program, at least in the entry for this. So he must have had a program, or she must have had a program for computing this, but we don't have an official one, and it would be nice to have more. If you don't allow exponentiation, so only plus minus, multiply and divide, you get a classical sequence, A140606, and that begins 1, 6. The reason it's 6 and not 8 is that these last 2 expressions, A to the B and B to the A, they're not allowed anymore. And this sequence, submitted by someone called Tu, has 300 terms, but there's no program. And there are several references in Chinese. If there are any people in this class who can help with this, that we need the authors' names, the titles of these papers, and what's more, we really need a program. 300 terms is a lot for a fairly subtle sequence. It would be nice if they were checked. So here are some examples of rejected sequences. A typical rejected sequence would be the list of even primes. Okay, there's only 1. That's a pretty stupid sequence. That's not allowed. We have our standards. Sequences must have a few terms, unless they're really exceptional. So the top one here, primes of the form factorial k plus 7. That's a little bit.
What about the empty list? Does it exist?
The empty list of?
The empty list, the list with no entries. The most important set in set theory is the empty set.
That's true. Yes. That's not a sequence, though. I mean, it's the empty sequence. Yes, that's a good point. We have the sequence of all zeros, which is sequence A4. But the empty sequence doesn't quite fit into the database. That would be
because the even less elements than the number of even primes.
Yeah. But this one here, the first example here is primes of the form factorial k plus 7. That's a bit like even primes, because factorial k plus 7 is not going to be a prime once k is bigger than 6. Because factorial k is divisible by 7. So that's a kind of a stupid sequence. So we rejected it. It only has 4 terms. You can get 13, 7 plus 6 is the first example. K equals 3, you get 6 plus 7, you get a prime, but you only get 4 primes, and then it stops. So it's kind of a stupid sequence. So we rejected it, but on the other hand, we created 3 other sequences following the idea from this. So we gave this person credit for having prompted these new sequences, one of which was a triangle, an array in which the nth row lists primes of the form, that should say factorial n. No, sorry, the nth row, the fourth row, the fourth prime is 7. So the fourth prime is the fourth prime plus factorial k, 7 plus factorial k. So his sequence became the fourth row of an array. And each row has a finite length, and that's a sequence. And we said this was following a suggestion from whatever his name was. So that was rejected because basically it's stupid, but we transformed it into 3 interesting sequences. That's what the editors do. Another sequence that was rejected was primes of the form 50 to the k plus 51. And we have a rule, you can't have a sequence that depends on a large parameter, like primes that begin 1, 2, 3, 4, 5, 6. Be stupid. It has to be interesting. So that was rejected because it depends on a large parameter. And there were only 3 terms and probably no more. So yeah, we don't need it. And then there was a proposed comment for the triangular numbers, which was not really relevant to the triangular numbers. If we tried to keep track of all the references to powers of 2, it would be hopeless. So the big core sequences like powers of 2, triangular numbers, primes, we don't try to put down every single occurrence of them in the literature. So that was rejected for that reason. And then when the sequences are rejected, we always make a note of them on a wiki page of deleted sequences. And there are abbreviations that, to save time, NOGI means this is not of general interest. And NFO means it's not for us. It's not for the OEIS. It's not up to our high standards. And RIFO is retired in favor of some other sequence, which is better, usually because there was something wrong with the new submission. Maybe it missed a term, or it had an error in it, or it was just a simple duplicate. You'd be surprised how often we get duplicates submitted. It's very easy to be confused about what is actually in the database. And then there's a list of citations. And as I said, we're now up to 10,000 citations, and they're arranged alphabetically. The citations from people whose last name begins with A, the site A, I've extracted just to show that people like the OEIS. I've put a few selected comments at the beginning of each of these 26 or so citation pages. And typically, this is a fairly typical thing. They say this paper, this theorem would not have existed except for the OEIS. And then underneath it, there are, for people, last names beginning with A, there are quite a lot, several hundred, rearranged alphabetically by last name. So this is just a selection from that, highlights from that page. And I got an email 4 years ago from someone that I used to know who said that he's an algebraic geometer and he doesn't usually look at the OEIS, but he was remembering back in the 1990s, he was at high school in Oregon and he got interested in sequences, sent in some sequences, and we encouraged him, and his teachers encouraged him, and he went on and he studied mathematics. He got his PhD, and he is now an algebraic geometer at one of the big Ivy League colleges. And he says, I want to thank you for engaging with an 18-year-old kid. And I doubt if I would have become a mathematician without the OEIS. And when I stepped down as president, I wrote to...
How come it's XXX? Who is this guy?
I didn't want to mention his name because I don't have permission from him to
Okay, no, it's
use.
very nice of him, but it's a little bit dismissive. He said, this is good stuff for high school kids, but now I'm a highbrow and don't do it anymore. So I don't like it that way.
Yes, true. Well, yeah, it's true. But when you look at books in algebraic geometry, they don't tend to have very large numbers in them. So not so many sequences. So when I stepped down as president, I mentioned to one of my friends that I was worried about the future of the OEIS, because after all these years, what's going to happen to it? And he said that he thought that the OEIS will last at least as long as the internet. There are three other comments at the bottom here, one of which he said, I forget who sent this in, somebody famous. I hope the world will support the OEIS and ensure its survival for a long time. So when you folks launch your first startup and make your first $1 billion, keep the OEIS Foundation in mind. Gerrymandering. I'm going to come back to this. I want to go to the
conjecture. Is it Don Knuth, this famous computer scientist?
I don't have permission to say who it was. It's somebody you know. Yeah.
I have a conjecture.
So the last topic, which I want to get to right now, other topics. There's an really impossible sounding problem called the stepping stones problem. And I made a YouTube video that you can see, and there are a lot of unsolved problems there. And there's a link to the Code Golf website for programs. It's well worth looking at. We need more terms. It's a really interesting question. Another one is, how many squares can you make if you put down endpoints in the plane? Sequence 51602, an old sequence, but it recently resurfaced, and we know a lot more. And Stan Wagon's problem of the week is what I want to talk about right now. But the fourth thing here is, here are 4 sequences that I would really like to know a formula for. They're simple geometric sequences. We have hundreds of terms. We have the explicit terms. There's a simple geometric definition, but we don't have a formula. I would very much like to have formulas for those 4 sequences. They're typical examples of things you say, it looks tricky, but there should be a formula. There should really be a formula. The third one, Stan Wagon's problem of the week. Stan Wagon has, it's a series of problems that.
Neil, a formula is very vague. A formula, there's always a formula. Sigma 1 going over.
Yeah, of course. Yeah, sigma, you can always use Lagrange interpolation and find a formula, or you can just repeat the last term. Sure. That's why I didn't want to offer money, and then I'd have to put in conditions. You have to be so yeah, I agree.
A good formula.
A good formula, a formula that anyone would agree is a formula. No Lagrange interpolation. Yeah, Stan Wagon has continuing a tradition. He's at McMaster College, and there's been a tradition now that's been going on, I think, 50 or so years. The problem of the week. Now it's not every week anymore, but problem of the week 1321, an impossible sounding problem. And here's the problem. You want to pick a set of n numbers, n different integers, such that the sums of pairs, every sum s plus t, is a power of 2. As many as possible are powers of 2. So suppose you can pick 2 numbers. How many, 2 distinct numbers, how many ways can you get a power of 2? Well, there's only 2 choose 2 possibility. So take 0 and 1, the sum is 1, it's a power of 2, you can't get more than 1. So W for Stan Wagon, W of 2 is 1. W of 3, you can get 3, matching the upper bound by taking -1, 3, and 5. Those are 3 integers. The sums in pairs, -1 + 3 is 2, -1 + 5 is 4, and 3 + 5 is 8. Those three sums are all powers of 2. The sums don't have to be distinct, but the numbers have to be distinct. And we want to get as many powers of 2 as possible. Pretty simple question, you might think. The trouble is, how would you program it? And Steinwagen's problem, he has an extensive mailing list. This has been going on a long time. Many people looked at this problem. Nobody could find the fourth term. Open question. The conjecture was that you can get 4 powers of 2 by using, for instance, -3, -1, 3, and 5. But how would you program this? This shows the limitations of the experimental approach. You can program it. You can say, all right, let I go from -infinity to infinity, and let j go from -infinity to infinity, skipping I, and so on. How many powers of 2? It is very tricky to program it. Many people worked on this. Nobody could solve the problem of finding W of 4. Until last month.
I have a question about it. In the old days, we had a minimum of 5 terms for a sequence. So this is exception?
No, not really, because the best we could do was to use integer programming, mixed integer programming, and set bounds. And
no, but you only have 3 terms, right? So far.
We only have 3 terms. Yeah.
That sequence is an OEIS?
Well, let me finish.
Yeah.
So various people on various mailing lists used integer programming, and they found that if you assume that the numbers are bounded between -n - 3 and +n + 3, you would get what looked like all the solutions that were known. That looked like a good working rule. So we created a sequence that had, I think, 100 terms, 347301. It has 100 terms. The definition is, it's this plus the assumption that the numbers are in the range plus or minus n - 3. So that was a sequence, and the conjecture was that that gave the exact answer for all n except 5. It was a sequence, it was well defined, and it probably was correct. So we got a sequence from it, but it wasn't too satisfactory. So last month, I got an email from M.S. Smith that almost solved the whole problem. And he uses, or she, I don't know this person. There's a theorem. Smith's theorem is that if you form the obvious graph, make a graph whose nodes are the elements of the set and join 2 of them if the sum is a power of 2. The theorem is this graph contains no 4 cycle. You can't have a 4 cycle in the graph, and the proof is not that difficult. Look, we've got 4 numbers, S1, S2, S3, and 4. Their sums of S1 plus S, we've got a C4, a 4 cycle in the graph. That means this sum is a power of 2, this sum is a power of 2, and so on. We've got 4 powers of 2. Let's call them B1, B2, B3, and B4. So B1 is a power of 2, and it's S1 plus S2, and B2, and so on, is S2 plus S3. And we know that the S's are distinct. So that means that B1 can't equal B4. Because if B1 is equal to B4, that would mean that S2 is equal to S4, but it's not. The S's are different. So the adjacent B's are distinct, okay? But now look at the sum of the opposite pairs. B1 plus B3 is S1 plus S2 plus S3 plus S4. And so is B2 plus B4. So we have 2 sums of powers of 2 that are equal. Now, if you have a binary number, if you have the sum of 2 binary numbers, look at its binary expansion. Sum of two decimal numbers, look at its binary expansion. If there are two powers of 2, it's got 2 1s in it. And those 2 1s identify the powers of 2. This is what's called a Sidden set. The Bs have the property that you can't have powers of 2 have the property that no sum of 2 pairs can equal any other sum of 2 powers of 2. So because we know that B1 plus B3 is equal to B2 plus B4, look at the binary expansions of that number. That means that B1 must equal either B2 or B4, but we've proved that can't happen. So this is a contradiction. So you can't have a 4 cycle. That means that W, this mysterious number, is bounded by the maximum number of edges in a graph with no 4 cycle, which happens to be a sequence, a classical sequence, A6855. And we know a lot of terms of this sequence, and they match the lower bounds for the first 9 terms. So now we know 9 terms of this sequence. The 10th term is still a mystery. The C4 number is 16, and the best we know is 15. So it would be nice to knock that off. It also gave us an asymptotic upper bound, n root n over 2. So with this one theorem, one bit of thinking rather than computing, I always fall into this trap myself. You start off by collecting data, but it really does help after a while to come up with a theorem. This took us from knowing almost nothing to almost a full solution. All right, let me go back to the gerrymandering. Where are we? Gerrymandering. You all know what gerrymandering is. It's in the newspapers every day. It's extremely important. And the simplest version of the question is, what's the smallest number of votes you need to win, even though you don't have a majority? And here's an example. I've got 2 parts to this. The first part is very easy. The second part looks like it's pretty hard. For the first part, we're going to pretend we have the following rules. We've got n voters, and we've got 2 candidates, little a and big B. And the voters are divided up into districts. And each district is a winner-take-all. And you are going to be able to draw the districts yourself, and you want to make sure you can win, even though you don't have many votes. Let me have a drink of water here. So here's an example. Suppose we have 36 voters, and we are allowed to draw the districts ourselves. I mean, we meaning we're the B candidate. The B candidate is going to draw the districts, and he doesn't have many votes. He's quite unpopular, but he wants to make sure he wins. So let's say that we have the 36 voters. The voters are in a 6x6 grid, and we only have 14 votes out of the 36. We're not that popular. But we get to draw the districts, and we're going to win because we can draw the districts in such a way. What we say is, all right, the rules are they're going to be 3 districts, and each district is going to have 12 voters, and whoever wins 2 of the 3 districts wins the election. And then you carefully draw. You've only got 14 votes, so you carefully draw the districts so that you win 2 of the districts, and your opponent wins the other one. And you can do it, and this gives a sequence, the minimum number. It depends on the divisors of n, obviously, and there's an explicit formula, and depends if n is a prime. You can't do, you have to be honest, you actually need a majority, but if n is divisible, like 36, if you can divide it up into a group of smaller districts, then you can cheat and win by carefully drawing the districts. And there's a sequence that gives A 3, 4, 1, 5, 7, 8 gives the details. if it's a square number. And if it's a general number, it's 341721. You can look up the details. And there are now quite a number of groups around the country that are studying gerrymandering and redistrict officially. There's a group at Princeton called the Princeton Gerrymandering Project, we bridge the gap between mathematics and the law to achieve fair representation through redistricting reform. And I think there should be more sequences coming out of different aspects of this problem. And it's also a very interesting subject to study anyway, a combination of combinatorics and geometry and the law. There's a group at Tufts, headed by Moon Duchin, and there are various. Her group has many papers, many interesting articles about this. But the second part, what you notice, the trouble with this picture here is that the districts don't have to be connected, which seems cheating after all. I mean, they're supposed to be districts. You can't just draw them in a random way. What if you require that the districts are connected, officially a rook connected, so a rook can edge connected, so that you can walk from one square to another without just by crossing square boundaries. So that leads to an interesting question, which is, how many ways are there to cut up? Let's just look at squares. Suppose you have a K by K district and you want to cut it up into equal regions, equal area regions. They don't have to be congruent, but you want equal districts. So you have a 3 by 3 board. How many ways can you cut it up into 3 equal districts? Well, you could have 3 straight lines, and you could do that in 2 ways. You could cut it up like this in 4 ways, or like that in 4 ways. So the answer is 10. So T of 3, 3, number of ways to cut up a 3 by 3 chessboard into 3 equal area regions is 10. So that's the sequence. And here's what we know. T of KD, it's a sequence. Here are the relevant sequence numbers. And the 10 is here. That's the number of ways of cutting up a 3 by 3 board. Let me show you. For a 4 by 4 board, how many ways can you cut up a 4 by 4 chessboard into 2 equal area regions? Well, the answer is 70, and I worked it out by hand because I wanted to check how you do it. And well, I made up some codes to describe these, just to make sure. The hard part is to make sure that you've caught them all and that they're all different. So this one here, if you read it from left to right, you've got squares of 1, 1, 1, and 4. So that was my code. And then B is the number of, what's B? B is the number of boundary points. B is 4, B here, I forget what this is. B is 7. And so on. So I made up some codes and I checked, and there are indeed, as everybody says, there are 70 ways to do this. And so we know some things about this. We know, what do we know? One thing we do know is the famous dimer problem. How many ways can you cut up an n by n board into dominoes? Dimers, physicists call them 1 by 2 polyominoes, 1 by 2 blocks. And there are 36 ways of dividing up a 4 by 4 square into dominoes. And the nice thing about this is there's a beautiful explicit formula for the number of ways to do this. See, it's sequence A4003, Castellan, 1961. Amazing that there is a formula. Very surprising. So that's the second to last entry in each row. and up to 8 by 8, we know all the values. Oh, up to 7, we know all the values. The first unknown case is 8 by 8. Take an 8 by 8 chessboard, a standard chessboard. How many ways can you cut it up into 2 parts? This is not known, and it will be very nice to know the answer. And a homework, if you want, work out what this number is, or that actually might be hard, but how big is it roughly? I don't know. Roughly, how large is this? This column here is a sequence. It goes 2, 70, 80518. I showed you the 70 for cutting up a 4 by 4 chessboard. A 6 by 6 chessboard, you can cut it up in 80518 ways. But 8 by 8, that's your homework. And all right, even if you can't do it, how would you program it? Can you parallelize it? And about how big is it? How long is it going to take? And I mentioned that Paul Zimmerman and his colleagues in 2020, they solved one of the RSA challenge problems, and it took them 2,700 core years. And they used, obviously, a lot of computers in parallel. How long will it take to find out the answer for this? That's a homework assignment. I showed you that, and I showed you that. And that's the end of it.
What is the A number of the second column?
Yes. It's one of these 4. I don't remember which one.
Okay, thank you.
Yeah. You know where to look it up. Any other questions before I move on to the last segment, the facial recognition segment? All right.
Yeah, go ahead. Neil, give them a few seconds to think of questions.
Yeah, yeah.
Anybody has questions about this?
Or anything else?
Yeah, and you're welcome to unmute yourself any minute if you have any questions. Robert, do you have any specific questions about what Neil talked about so far?
No, nothing yet.
Okay.
Okay, in that case.
Okay. Anybody else? Another sense? Okay, thank you.
I was going to use this opportunity at some point from a long time ago, though, to ask you to finally explain what the second part of the offset of a sequence means, but maybe we can come back to that at the end.
No, and it's a perfect time to ask that question, because I'm going to be talking about LES sequences and facial recognition. So you can order sequences of non-negative integers in lexicographic order, right? And you say blank comes before 0 because it comes before 1, and so on. So sequences that begin 1, 2, 4, 6, they come before 1, 2, 5, 6, and so on. And 1, 2 stop comes before 1, 2, 0 because a blank comes before 0. So you can virtually think of all the sequences of non-negative integers as being sorted in order. And in the OEIS, and even when it was on punch cards, they were sorted in order. And the rule was you would throw away all the numbers. You look at the absolute values. We ignore minus signs, throw away all the numbers, all the terms in the sequence, the initial terms that are less than 2. So we look for the first term in the sequence that's bigger than 2, bigger than 1 in magnitude. So here's the EKG sequence. It begins 1, 2, 4. If it had begun 1, 1, 1, 1, 1, minus 1, 1, 2, we throw away everything up to the first term that's bigger than 1 in magnitude. And that position of that's the second offset. So it's 2 here. You start sorting this sequence. It comes into the sorted order at its second term. You look for where it sits. So that's the second offset. And so all the sequences in the OEIS are sorted lexicographically in this way. And when you look at a typical entry, you'll see a line that shows the sequences that come before and after it in the lexicographic order. And that's useful if you're not quite sure of a term, but you know the first few terms. Okay, so let's go back to.
And Neil, in the very first edition, the sequences were already arranged lexicographically with some convention.
Yeah, that's right. And what's more, I left out the minus signs, which was, yeah, I regretted doing that, but there didn't seem to be any good way of sorting them on punch cards with minus signs. Anyway, that's how it was. So we have a lexicographic order. Now my lexicographic order is going to be, I don't throw away the small terms now. In this, from here on in this talk, lexicographic order means this. We're only looking at non-negative terms, sequences with non-negative terms, and the rule is that blank comes before 0, comes before 1, and so on. So there's a very interesting class of sequences that I call the LES sequence, and this stands for lexicographically earliest infinite sequence of distinct positive numbers, such that, I'm assuming positive now, and infinite, because otherwise things get a little messy. The lexicographically earliest sequence that satisfies the EKG rule, every number has to have a common, every term has to have a common factor with the previous term. That's the rule. The EKG sequence, I started off with that. It's the LES sequence such that the GCD of the nth term and the previous term is bigger than 1. That's the rule. If I didn't put infinite, then the answer would be 0, stop, or 1. It would be a finite sequence, because the finite sequence, I guess if I'm insisting on positive, 1, the stop would be the earliest. But so you put in an infinite sequence to make sure that it makes sense. And so that's the example of the EKG sequence. And I showed you its graph. Here it is, 3 straight looking lines. There's a variant on that called the Yellowstone, where you change the rule. The Yellowstone is each term has to have a common factor with the term that's 2 before it, but it must be relatively prime to the previous term. That's the Yellowstone sequence. And again, it has a nice simple graph. And Scott Shannon in Melbourne turned that around. Yellowstone backwards becomes Enoch's Wally, which could be the name of an Australian politician, typical Australian name. He's in Melbourne. I used to live in Melbourne. And Les was the most famous Australian poet, Les Murray. So there's an Australian theme here. The Enoch's Wally sequence. It's like the EKG sequence. You've got to have a common factor with the previous term, and you have to be relatively prime to the term before that. That's the rule. The graph looks like this. It's got straight lines. It's not bad. It's a bit messy, but you can sort of see what's going on. And now I can switch over, I think, to the full view. I do play yet. Okay. Okay, so I've given you 2 examples of EKG sequences. For each of these these LES sequences, for each of them, there's a set theory version. There's a number theory version, which is the version I just showed you, and there's a set theory version. The set theory version replaces, instead of having a common factor, you have a point in common in the binary expansion. So the set theory analog of the EKG says that the binary expansion of the nth term must have a 1 in some position where the previous term has a 1. The binary expansions have to overlap. That's the EKG in the set theory version. And again, we always pick the smallest number. So look at it. We begin with 1 because there's no rule, there's nothing wrong with beginning with 1. We don't have to backtrack. So we begin with 1. The next number, so that's 1 in decimal. The next number, the binary expansion, has to overlap with it. So it can't be 2, but it can be 3. So it must be 3. So it goes 1, 3. and then we can have 2, and then 6, 4, 5, and so on. And this is the set theory version of the EKG sequence. And if you look at the graph, it's not bad. If you look at the terms, you can see what's happening. It goes 1, 3. After you get to 8, after you get to 1, 1, 1, you can see there's a pattern that holds. After 1, 1, 1, the next term is 1, 0, 0, 1. When we get to the all ones vector, 2 to the k minus 1, the next term is 2 to the k plus 1. So after 7, we get 9, and then we get 8, 10, 11, 12, 13, 14, 15. After 15, we jump to 17, and then we get all the numbers up to 31. So we get all the numbers in order, basically, except for a couple of flips when we get to a power of 2. So when you look at the graph, here's 1,000 terms. It's a dead straight line, as far as you can tell. Easy, okay. But now, this is the really interesting thing. Look at the set theory analog of the E0-Wally. So now, the rule is, well, we've got to have a 1 in common with the previous term, and we've got to be disjoint from the term that's 2 back, all right? So we begin 1, 3, just like we did here. What comes after 3? We've got to be disjoint from the 1, from the thing that's 2 back, and we've got to overlap with the 3. So we need a 1 and a 0. So why isn't it 2? Why doesn't it begin 1, 3, 2? It's disjoint. Any answers? Well, the answer is, if you made it 2, you could try making it 2, but then you couldn't extend it. Because if it was 1, 3, 2, if that 1 was missing, there's no way we could get the 4th term. Because there's no way to find a number that overlaps the previous term that doesn't overlap the term before. So here, the lexicographically earliest infinite sequence, bytes, you've got to allow the sequence to be infinite. So you can't do the greedy algorithm.
You have to backtrack, right?
You have to backtrack. So here we didn't need backtracking. Here and in many of these, you have to do backtracking. Actually, you can dodge the backtracking by saying, all right, I can outsmart this. I'm going to say the next term, it's got to be disjoint from 2 back, it's got to overlap 1 back, and it has to have an additional 1 somewhere. And you look for the smallest number with that property, and then you don't have to backtrack. It's greedy. The greedy algorithm subject to that, modified greedy algorithm. But you can say explicitly what the next term is. It's the smallest term, which is disjoint from 2 back, overlaps 1 back, and has an additional 1 in it somewhere. And you pick the smallest. So
do we have a good understanding for which LES sequences do require backtracking versus not?
No, not really. No. Eric Angelini has submitted many lovely variations, and some of his take a lot of backtracking. Some of them are complicated enough that we can't be sure they even exist. Yeah, but this particular class that I'm talking about in this segment of the talk, you can dodge the backtracking. You can dodge the backtracking worry and say explicitly what they should be. The trouble is understanding what's going on. So, okay. So we got the sequence, right? There it is. Look at the graph, and you say, "What the heck? Look at that graph. That's incredible." When I saw this, I thought, you can see it's fractally. It's got these things that look like distorted, whatever. It's fractally, but it's a mystery. What on earth is going on? There's a theorem. This sequence was actually, I think, sent in by Nathan Nichols, and he has a proof that this is a permutation. And I haven't checked it. One of the homeworks, if somebody would really like to understand this stuff, check his proof. It needs to be done, and I haven't had time. Prove that the set theory analog of the E0-Wally sequence is a permutation, that every number appears. And then if you can do that, see if you can prove that E naught Wally itself is a permutation. We do not have a proof of that. And okay, so now I'm getting towards the facial recognition stuff. I was worried about this sequence. So I started searching and I found a simpler version that has the same graph. You can see that, where are we? That and that look pretty much the same. And there's a reason. So this is sequence, whatever it is. It's A109, 110, 105, 110. It's 109, 812. Here it is. So this is like E naught Wally, only simpler. And what is it? And this has, this is a set theory version. And the rule is very simple. Now, it's on my screen, it's covered up. I'm going to get out of this. Okay. The faces were covering up the crucial thing here. This is a very simple sequence now. This is not E naught Wally in set theory. This is just the integers in set theory. So sequence 27 is the natural numbers, 1, 2, 3, 4, 5, 6, 7. That's an LES sequence defined by the property that each term has to be relatively prime to the previous term. Start with 1. What's the smallest number that's relatively prime to it? 2, and so on. You get the natural numbers. Do that in set theory, and you get this sequence. I actually call it the Tetris sequence. The rule is you've got to have, you've got to be disjoint. That's all, disjoint from the previous term and a new number. So after 1, we get 2. After 2, we get 4, and then 3 and 6. And that gives this. And so this, the natural numbers are a pretty basic sequence. This has to be a pretty basic sequence too. And its graph is this mystery. And here's another picture of this graph. Now, this one is another picture with some colored things. A group of us have been studying this sequence really hard, and we've made some progress. Remy Segrist noticed that if you plot this sequence as n comma log of a of n, it looks like this. If you plot it as a of n against a of n plus 1, using the plot 2 thing, you get something that looks like this. This is a different way of plotting the sequence. And this is starting to look reasonable, because this is really just the Sierpinski gasket. You know that the Sierpinski gasket is Pascal's triangle, red mod 2, and it looks like this. It's infinite, it's a famous fractal, the Sierpinski gasket. And Lucas' theorem tells you exactly where the dots are. That it's the binomial coefficient n choose k. It's 1 if and only if k is a subset of n in binary expansion. And if you plot this as in a different way, write down the graph whose points are x comma y, where x and y are disjoint in binary. This is Sierpinski's gasket, written as a corner shape. And that looks very much like that. And so that and that look very similar. So we sort of understand this. And the reason I found this was by finding that the graph of that sequence, the Tetris sequence, matched very closely the graph of the E naught Wally set theory version. And I would like to propose as a problem, a project, something you might think about, maybe even a summer project. How would you automate this? We have 350,000 sequences, and many of them have B files. Suppose we made a virtual movie of these graphs, and then it could be like the science fiction movie where you see they make a composite of the criminal's face, and they say, let's see if he's in the database. and they run it, you see the faces, millions of faces going through at a high speed, and suddenly it stops and say, there, that's him, we've caught him. Well, I would like to do the same thing with sequences. Now, in 2010, yes. In 2010, Tony Noe made a movie, the OEIS movie, and he made a graph. This is a real movie, it's on YouTube, of 1,000 terms of 1,000 sequences. Well, I'd like to do this virtually. So these would all be 10,000 terms of 10,000, of 100,000 sequences. Make a movie, virtual movie, and then match it using some kind of facial recognition software to try to find a match. And where are we? So faces are, trouble is faces are pretty simple. All faces more or less look alike, and there are standard measurements that you make. Sequences come in a lot of different ways. So still, in many ways, they're simpler than faces because we're given them in data format. That's my last slide. It's a project. You could, if I would like to know how would you use facial recognition techniques to recognize sequences? I'd better stop there. It's 11:30. Any more questions? Any questions?
Let's not unmute yourself and thank Dr. Sloane for a beautiful and fascinating and very, very challenging talk.
Thank you.
We have plenty of time for questions, either about the content of the talk or general about OEIS.
Neil, there was a slide a few slides ago. We went by it pretty quickly. It had colors on it and letters like A, B, and C. Could we see that again?
Yeah, right.
I don't think I understood what that was.
No, I didn't explain it. Where are we? We're down here. Okay. It must be. It's this one.
Yes.
Yeah. Well, it's this one. When I looked at this, I saw these great cavities. It's going along. Basically, it's a solid triangle. That's a Sierpinski triangle. It's Pascal's triangle, really, but it has these great gaps in it. And if you're traveling around in France or Spain, where France meets Spain in the Pyrenees, there's a wall of mountains, and near Gavigny, there's a famous break in the mountains called the Brèche de Roland, of the Song of Roland, the famous Charlemagne, whatever he was, and it was in the time of Charlemagne, and it's called the Brèche de Roland. And I have been trying to understand where these breaks occur. And this picture, where are we? This picture is related to where the breaks are. Not quite, but actually this picture shows the breaks a little bit better. You can see a break here. This graph uses different colors for even and odd. There's a break. Anyway, that's what that is.
I have a question.
Yes.
In the EKG sequence,
Yes.
I noticed that the prime number, like say 5, to the left of it is 10 and to the right of it is 15.
Yes.
And it seemed like that's the case for most of the primes on the list, all the ones that I saw. So do we have a proof that that always happens, or does that not always happen?
Yes. It's a good question. When Lagarius and Rains and I wrote that paper, we could not prove that. We left it as a conjecture. It seemed to be true. We always, except for the prime 2, primes always come in the form 2p, p, 3p. It's got to be one or the other. But in fact, it's always 2p, p, 3p. And 2 Polish mathematicians found a proof of that fact. So it's a theorem. Yes. And there's a reference to it in the EKG sequence. one of the references there. But I've never studied. The proof is tricky. Even our paper was extremely tricky. Getting bounds, getting the linear bounds on the sequence was not easy. It was some fairly heavy analysis needed. And that paper continued the analysis.
Do you think that there's going to be an easier proof, or maybe not?
It's possible, yeah. There could easily be a clever proof. Yeah.
But the fact that there are 3 straight lines is still open, right?
That's right, yes.
Yeah.
Yeah. They're not really straight. They're more of the form
Asymptotically.
constant. It's x times 1 minus 1 over log x kind of thing. Instead of y equals 6x, it's y equals 6x parens 1 minus 1 over log x. It's that kind of thing.
So close, but not.
Yeah, essentially straight.
More questions from the students to Dr. Sloane? So please consider becoming at least registered, but hopefully also associate editors. And great. So thanks so much for really fascinating talks. And we're gonna record it. Robert will record it, and I post it as soon as possible. And the homework for today is everything is optional, but to do some of the assignments that Neil gave in this.
Yeah, I hope you'll do that. Thank you. I'll also send you the slides, Duran.
Yeah, be great. Thanks so much. Okay, thank you. As you know, this is the last online class. I hope to see you on Monday. This ends this class. Thanks so much, Neil, for a great talk. Okay, bye-bye.
Thank you.
Thank you. Bye-bye.
Bye, everyone.
Yeah.